Hello, this is video number 23 on my single variable calculus 2. In this video, we're going to talk about alternating series test and the absolute convergence test. So first, the alternating series test. An alternating series is a series that terms alternate between positive and negative. So an alternating series test tells us that if you have an alternating series and you look at the positive portions of the terms and the positive portion decreases and it approaches zero, then the alternating series would converge. Note that the alternating series doesn't tell you anything about divergence of the series. It only tells you that the series converges if it satisfies these two conditions. So let's do a couple of examples on this. The first example is the sum of negative 1 to the power of n over n natural log of n. Negative 1 to the power of n becomes positive when n is even and becomes negative when n is odd. That's why this is a series that is alternating. So let's look at an. An is the positive portion, which is 1 over n natural log of n. We would have to check two different conditions. This is in fact decreasing because the denominator is increasing and converges to 0. So because it converges to 0 and it is decreasing, by the alternating series test, the series converges. So it's actually a pretty simple test. We have to check that the sequence converges to 0 and the sequence is decreasing. So second part, we have negative 1 to the power of n minus 1, 2n plus 3 over 4n plus 5. So if you look at an is 2n plus 3 over 4n plus 5. But if you look at this one, this doesn't converge to 0. This converges to 1/2. Well, that means that we cannot use the alternating series test. But we can say that negative 1 to the power of n minus 1, 2n plus 3 over 4n plus 5 definitely does not converge to 0, because if it did converge to 0, then when you took its absolute value, it would converge to 0 as well. So that means by the test for divergence, the series in fact diverges. Okay, let's look at the next topic. So if you look at the alternating series, we can approximate the alternating series by its partial sums. Now the error for approximation of the alternating series by its partial sums is the next term, is the following term. You have to make sure that it satisfies the conditions of the alternating series test, which means the series is alternating, the terms approach to 0, and also they are decreasing. So let's look at one example on this one. First, show that this series converges. Well, how do we show the series converges? First of all, note that this is an alternating series. So an is 1 over 3n plus 4. So we'll have to show that this is decreasing. Well, 3n plus 4 is increasing. Therefore, this is decreasing. And also, an converges to 0. So that means by the alternating series test, the series in fact converges. So that's the first thing. The next thing we're going to do is, they said, find a value of n where the nth partial sum approximates the alternating sum with an error not exceeding 0.01. Well, they told us that the error, we saw that the error is less than or equal to the n plus first term. The first term is obtained by plugging 1 in there. So the n plus first term is obtained by plugging n plus 1 in there. So we have this, and we want this to be less than 0.01. They said not exceeding, so it would be less than or equal to. So this is 1 over 100. If we take the reciprocal of both sides, we get 3 times n plus 1 plus 4 is greater than or equal to 100. Let's distribute that. We get 3n plus 7 is greater than or equal to 100. Subtract 7. We get 3n is greater than or equal to 93. Divide by 3. We get n is greater than or equal to 31. So n equals 31 is in fact the best answer. So if we want to get an approximation that the error does not exceed 0.01, we have to take the first 31 terms and add them up. Let's look at the next test. The next test is the absolute convergence test. It tells us that if sum of absolute values of a sequence converges, then the sum of the terms of the sequence also converges. Test for convergence of this series. So if we look at this series, it's difficult to find out whether the series converges or not until we take the absolute value. So if we take the absolute value of that, we can compare this with 1 over n squared plus 5. But then this is also less than or equal to 1 over n squared. So what does it mean? It means I can use the comparison test. So we're going to have to use basically the p-test first. So the sum of 1 over n squared converges by the t-test, and here t is equal to 2, which is greater than 1. So that's one thing. Now, because of the comparison test, by the comparison test, I can say that the sum of absolute value of sine of n over n squared plus 5 converges. And because this converges, I can drop the absolute value and say by the absolute convergence test. So by the absolute convergence test, the series would converge. The sum of sine of n over n squared plus 5 also converges. Now, as we saw, if we take the absolute values of the term of a series and it converges, then the series itself converges. That phenomenon is called absolute convergence. So if you have a series that when you take the absolute value of the terms, you get a convergence series, we say the series absolutely converges. If the series converges, but the series of absolute values diverges, we say it conditionally converges. Let me do 3 examples on this one. Okay, so the first example is sum of -1 to the power of n times n over n squared plus 1. We want to determine whether this converges absolutely or conditionally. So we're going to take the absolute value of the terms and see what we get. So if we look at that, that is n over n squared plus 1. Well, this is roughly n over n squared. So if I choose bn to be n over n squared, I can use the limit comparison test. So we're going to take n over n squared plus 1, and we're going to divide by n over n squared. So that's n squared over n. This is going to be n squared over n squared plus 1. Now we're going to take the limit of n squared over n squared plus 1 as n approaches infinity. Well, that is 1 because it's polynomial over polynomial, so we have to look at the leading term. Leading terms are the same. Now, by the limit comparison test, the series both converge or both diverge. Note that both of these two sequences are positive, so we can apply the limit comparison test. So now, how do we know if Bn converges? Let's look at the sum of Bn. Sum of Bn is sum of 1 over n. This diverges by the p-test because here p is 1. So that tells us that the given series, when you take the absolute value of -1 to the power of n, n over n squared plus 1, this diverges. So that doesn't tell us anything about this series itself because we don't know that this is absolutely convergent. We just know that when we take the absolute values, it diverges. So we'll have to test the series itself too. So let's look at this series. Now, if you look at this series, well, this is an alternating series. So this is an alternating series. So we'll have to find a way to see if it converges. Well, maybe it satisfies the conditions of the alternating series test. So let's take an as n over n squared plus 1. Well, first of all, this approaches 0 as n goes to infinity because that's just n over n squared when n approaches infinity. Now let's see if this is in fact decreasing. So let's take the derivative of this and see if it becomes negative. If the derivative is negative, then it would be decreasing. So we'll take the derivative with respect to n over n squared plus 1. That would be, the bottom is n squared plus 1 squared, derivative of numerator times denominator. So that would be 1 times n squared plus 1 minus derivative of denominator times numerator. That is 1 minus n squared over n squared plus 1 squared, which is in fact negative. So that tells us that an is decreasing. So it is decreasing and it approaches 0. So by the alternating series test, the sum of negative 1 to the power of n times n over n squared plus 1 converges. Now the series itself converges, the absolute values diverge, so the series converges conditionally. Okay, so let's look at the next part of this problem. The next part, we're going to have to do something similar. We take the absolute values and see what happens. So if we look at absolute values of negative 1 to the power of n over n squared natural log of n, that would give us the sum of 1 over n squared natural log of n. Well, natural log of n is more than 1, at least when n is more than e. And again, it doesn't matter what happens in the beginning of the series. So 1 over n squared times natural log of n is less than 1 over n squared if n is more than e. And of course, it is positive. So now we can apply p-test, sum of 1 over n squared converges by the p-test because p is 2, which is greater than 1. So by the comparison test, the other one also converges. So by the comparison test, the sum of 1 over n squared natural log of n converges. Okay, so that tells us that the given series converges absolutely. So the given series converges absolutely. Okay, let's look at the last part of this problem and then we will summarize. So the last part of the problem is n plus 1 over 2n plus 1, negative 1 to the power of n. So let's take the absolute value and see what we get. So we take the sum, negative 1 to the power of n plus 1 over 2n plus 1. So this is the sum, and we get n plus 1 over 2n plus 1. Well, what we know is that n plus 1 over 2n plus 1 approaches 1/2. So n plus 1 over 2n plus 1 approaches 1/2 as n approaches infinity. So this tells us that by the test for divergence, the series sum of n plus 1 over 2n plus 1 diverges. But what about the original series? Well, the original series also diverges because since the absolute value doesn't converge to 0, so absolute value of negative 1 to the power of n over n plus 1 divided by 2n plus 1, that doesn't converge to 0. So that means the sequence itself also cannot converge to 0 either, because if the sequence were to approach 0, then its absolute value would also converge to 0. So that means this also does not converge to 0. So by test for divergence, the series that we have, n negative 1 to the power of n plus 1 over 2n plus 1, diverges. So every series would have one of these possibilities. Either converges conditionally, or converges absolutely, or it diverges. And now we're going to summarize what we did. So we learned about the alternating series test. In order to use the alternating series test, we have to check that an is decreasing and approaches 0. Assume an alternating series satisfies the condition of the alternating series test. The error in approximation using the nth partial sum is less than or equal to the next term, the absolute value of the next term. The absolute convergence test tells us that if the sum of the absolute values converges, then the series also converges. A series is called absolutely convergent if the sum of the absolute value of the terms converges. A series is called conditionally convergent if the series converges, but the series of absolute values diverges. And that brings me to the end of this video. I will see you in the next video.